Thank you for the invitation to come and talk about this work. As you mentioned, the colloquium, so yesterday, for the benefit of anyone watching this on video who's not my mother, yesterday I gave a colloquium on this topic, which was essentially lecture 0. So that was an introduction to strong cosmic censorship. So if anyone's watching this wondering why I'm not citing their work, it was all cited in the colloquium yesterday, which was not recorded. So this series of lectures is going to be about the work that I've been doing recently on this topic with my collaborators, Oscar Diaz, Felicity Eperon, who's my student, who's just graduated, and George Santos. And so we wrote 3 papers on this topic last year. I've listed 2 of them here, which are the most relevant ones for this talk. If you're interested in reading a bit more detail, then I'd recommend starting with this paper because it has an extended introduction reviewing the history. So just to recap what I said in the colloquium yesterday, so strong cosmic censorship is basically the statement that if you have a charged or a rotating black hole with a Cauchy horizon in its interior like this, then that Cauchy horizon should be unstable. So this is the Penrose diagram I drew yesterday, for example, for a Rice-to-Nordstrom black hole. This is the black hole exterior. This is asymptotic infinity. This is the black hole interior. And the Cauchy horizon is here and here. This is the event horizon. And the reason we want the Cauchy horizon to be unstable is because otherwise we've got a failure of determinism because we can't predict what happens beyond the Cauchy horizon. So if we believe in determinism, then we can't have Cauchy horizons. In other words, they have to be non-generic so that when we perturb, it goes away. And the perturbed space-time does not have a Cauchy horizon. So as I explained yesterday, the mechanism behind the instability concerns late perturbations entering the interior of the black hole at late time, so perturbations like this, which trigger blue shift effect at the Cauchy horizon. So these late time perturbations out here are blue shifted up here, and that blue shift causes the perturbations to have a large local energy, which causes a large gravitational back reaction here, and hopefully destroys the Cauchy horizon, and recovering predictability so that the perturbed space-time does not have a Cauchy horizon.
So when it does destroy the Cauchy horizon, is the idea that the time-like singularity is just sort of bends?
Well, if you'd been at my colloquium yesterday, you'd know that this whole business of time-like singularity is just one of the things that could have been beyond the Cauchy horizon, but in fact there are infinitely many other things that could be beyond the Cauchy horizon. Okay, so there are infinitely many ways of smoothly extending beyond the Cauchy horizon. The thing you know about with time-like singularities is a particular way which you obtain by adding an extra assumption, which is analyticity. But if you just demand smoothness, there are infinitely many things up here you can put up here. Okay. Hi, Cindy. Good to see you. Yes. Shake hands with the director. Yeah. Always good sign. Really That's okay. So I was just reviewing the Cauchy horizon instability for charged and rotating black holes. The mechanism behind the instability is late time perturbations entering the black hole are blue shifted up here, and that blue shift causes a large gravitational back reaction, and in the perturbed space-time, strong cosmic censorship basically asserts that the perturbed space-time should not have a Cauchy horizon, instead it has a singularity. And there's pretty good evidence for zero cosmological constant that the effect of that perturbation for a two-sided black hole like this is to convert the Cauchy horizon into a globally null singularity. Okay, so that was a little bit surprising, as we now know it's globally null. It's not space-like, for example. Okay, so this is what I discussed yesterday in my colloquium. So just to write a few words about this. So the blue shift instability at the Cauchy horizon is triggered by perturbations entering the black hole at late time Okay, so these are late time perturbations from the perspective of the exterior of the black hole. I should emphasize that black hole is stable, of course, in the exterior region. A Kerr or a Royston-Nordstrom black hole is stable. It's only the interior which is unstable. But the key thing is it's the late time behavior in the exterior which is crucial here. So it's sensitive to the late time behavior of perturbations outside the black hole. Okay, so we need to understand the outside to understand what's going on here. Good morning.
I'm really sorry,
Yeah.
happy to have missed your colloquium yesterday, but the statement is that sort of regardless of the details of the late time perturbations, you get a globally null singular.
In the asymptotically flat case, yes. For this picture I've drawn here, where you have when you're considering, so you start off with initial data on a surface like this, say compactly supported initial data, and you perturb, then in that situation you get a globally null singularity, which was a bit surprising because back in the day Penrose would have said, well, it should be space-like, like Schwarzschild, but it's not, it's globally null.
And again, tell me later, but even in the old days when there was all this mass inflation story and so on, I thought generally the thinking was it would be space.
Yeah, so it's interesting though. So they were I think that idea of that it should be space-like kind of infected people's brains, but the evidence from the mass inflation is actually it's null.
Oh, I see. Is that right?
Yeah. So they showed that it's null. It's null at early time. It's true if you have a black hole which is formed by collapse, then it needn't be globally null. It could be, but it is still null at early time. It could become space-like further in there. Okay, so there's always this null bit early on.
Thank you.
Yeah. Why was it thought to be space? I think that people were just guided by the properties of the Schwarzschild solution. And the Schwarzschild solution, the problem with Schwarzschild is it's non-generic, even within the Kerr family. So you shouldn't use Schwarzschild as your example for guessing what would happen more generally. Anyway, so this was all for lambda equal to 0, but I'm going to be talking today and tomorrow about positive lambda, and on Friday about negative lambda. So let's just review what happens in these two cases. So for lambda equal to 0, we have power law decay outside the black hole. So these are what people call late time tails, which you have in any asymptotically flat spacetime. And this is pretty slow, and so strong cosmic censorship is respected. In this case, as I discussed in lecture 0 yesterday.
Could I ask, why is the, and this is an ill-formed question, but why is the power decay outside power law?
Why is it power law?
If you look at the quasi-normal mode spectrum, it has a gap.
Yeah, it's more to do with a branch point or branch cut in the green function. And so in the asymptotically flat case, there's a branch point at 0 frequency, which is the reason you get power law decay.
And can you say physically what's happening? Why is it so slow?
Why is it so slow? I mean, it's to do with gravitation. It's to do with radiation reflecting off the curvature of space-time far away from the black hole and being bounced back, basically.
I see. So why is it exponential then in ADS?
It's not exponential in ADS. I'm going to talk about this on Friday. It's well, okay. No, in ADS, if you fix an angular harmonic, it's exponential. But if you sum over all angular harmonics,
that's because things can rotate far.
Exactly.
Okay.
Yeah. And so in ADS, it's slower than power law.
Okay, fine. But so is there something like that here as well?
In the asymptotically flat
Yes.
case, no.
No.
There's no. In ADS, I'm going to discuss this briefly on Friday. But there's a phenomenon called stable trapping at infinity, which you don't.
And things far away just rotate.
Exactly.
Yeah.
In the asymptotically flat case, they just escape to infinity.
Right.
But in ADS, they can bounce off infinity and come back.
No, but why isn't the same bouncing off reason?
Because you can't bounce off infinity in an asymptotically flat space-time.
No, sir.
Yeah.
You said that the reason there was power law in flat space was
Yeah.
that of the potential barrier, it bounces
Yeah.
back and comes back.
Yeah.
So that would work angular momentum mode by mode.
Mhm.
Why doesn't that mean that even in ADS, mode by mode is power law?
Yeah, good question. I guess I haven't really thought about that. Since I haven't thought about it, I'm not going to answer it.
Mode by mode means
You
fix one angular
Yeah, you
harmonic,
fix one
then
angular harmonic, yeah.
Wasn't that the statement that then you still have an exponential decay?
Yeah, I'm asking why. Because the intuitive explanation for flat space was that the fact that it bounces back off the potential makes it power law.
Yeah.
That would be also.
Yeah, it's to do with the decay of the effective potential when you write down the equation.
Nature of the potential.
Yeah, so it's in the asymptotically flat case, it decays as a power law at infinity.
So it's the stuff going very far and bouncing back
Yeah.
that makes it power law.
Yeah.
I
So you have a different decay of the potential in infinity.
I was going to say, I mean, isn't it? I mean, in ADS, it's more like a box with two boundary conditions, and you have a Schrodinger-like problem with some, spectrum.
Yeah.
Here, the boundary conditions in asymptotically flat are that radiation goes off to, right? That boundary
It's
condition.
it's a little bit different.
One of them is
Yeah.
different.
But I think the real reason is the decay of the effective potential near infinity. It's the reason you don't get tails for fixed mode in ADS. Anyway, we still got positive. Let's forget about ADS until Friday, and let's look at positive lambda.
I have a question.
Someone got a question in ISTS?
Sorry, the question is, in a physical setting, you might try and ask if you actually had an observer who tried to cross the Cauchy horizon of some black hole. The thing that's physically relevant for that observer is that if somebody comes by 10 to the 10 years later and throws in a small amount of matter, that might not be infinitely blue shifted, but it'll be blue shifted enough to destroy this observer who fell in some time back. Right, so what I'm saying is that if you wanted to ask a physical question, doesn't it make the Cauchy horizon is certainly unstable because somebody could just come in much later and throw in something, even if that was a very small amount of. Isn't that true?
Yeah, but then we have to get into questions about who is this observer who can live forever and throw things in at late time. What are they made of? What equations do they satisfy? So the nice thing here is we're just talking about perturbations of a black hole using the fields at our disposal, rather than some agency who can act at an arbitrarily late time. And it really is an infinitely late time, right? It's really, if we cut this off at a finite time, then we cut off the instability.
In ADS,
That's true.
So it's really that we have this.
Infinity may not be relevant if you have an observer who has a finite strength, finite ability to withstand perturbations. So as long as something is blue shifted enough to destroy that observer, that's
Yeah,
sufficient.
actually it goes more the other way, which is something I discussed yesterday, which is even in the case when the Cauchy horizon does become singular, that singularity may not be strong enough to destroy an observer. And so something I discussed yesterday. So even though tidal forces diverge here, the cumulative effect of those tidal forces may still be finite, and in fact it is. And so yesterday I discussed what you have to do is ask whether the equations of motion for the observer can still make sense at the Cauchy horizon. And I explained that even in a weak sense, for lambda equal to 0, it's believed that they do not. So there's no sense that you can go beyond the Cauchy horizon classically for lambda equals 0.
Okay.
So just one follow-up question.
Yeah.
In ADS, isn't the field theory of eternal observer?
Okay, what do you want?
You can turn on non-normalizable modes in the field theory.
Oh yeah, okay. Again, well, we can discuss that on Friday, but that is something we did discuss a little bit in our paper. Yeah, but yeah, in ADS, if you give yourself that freedom, then you can trigger the instability. Yeah. Okay, for positive lambda, the difference now is we have exponential decay. So the decay is faster, which suggests that we're going to have a weaker instability. So this was first discussed in detail by Meller and Moss in 1990. So for positive lambda, we now have Reist-Nordström de Sitter, which I'll abbreviate to RNDS. So let's draw the Penrose diagram for that. So this is the same as before. We have an event horizon, Cauchy horizon. But now, instead of this being null infinity, we now have a cosmological horizon here, future cosmological horizon. If we go beyond this, we get to asymptotic infinity, which is now space-like. And similarly down here. And then the diagram just repeats as we go off. So we still have the Cauchy horizon. Let me introduce a little bit of notation for these various well, it depends where you start from. So if you start with a slice like this, then it's everything up to the Cauchy horizon. Okay.
But this diagram just repeats.
Yeah, it goes on forever. Or if you want, you can periodically identify. Let me call that CHR, the right component, and I'll call this CHL. I'll call this HR plus, and I'll call this HL plus. So I'm going to need to refer to these H minus and C minus. Okay, so in this setup, we want to ask if we specify initial data on, say, on this kind of surface, how does the perturbation behave up here near the Cauchy horizon? And the statement about exponential decay holds as we approach this point here in the region between the two horizons.
So if you periodically identify, then I mean, normally an eternal black hole creates a second universe.
Mm-hmm. There's a second universe here.
That's not part of just periodically identifying.
No, I'm not going to identify this with this. I'm going to identify this with this one. Yeah, yeah.
Sorry, Harvey,
Yeah.
the statement of exponential decay is on C plus or?
It's everywhere at late time in this region. So it's along here, it's along here, and it's as we go up this direction. So it's along on a foliation like this, basically.
Okay.
Yeah, yeah. And it refers to the exterior of the black hole. Okay. Good. So as I said yesterday, we can look at strong cosmic censorship both using linear theory and nonlinear theory. Of course, linear is easier, so let's do the linear case. So we're going to consider linear perturbations of Rice-Hamilton de Sitter. And these could be either a scalar field, for example, or we could look at gravitational and electromagnetic perturbations, which in this space-time, so they're coupled together, but you can get decoupled master equations for them. Okay.
Just for reference, what's
Yeah.
the Penrose diagram for short shield AD?
It's same as this, but with a space-like singularity across here.
These laws are node by node or overall?
The-
That you were mentioning?
Which are?
This, let's say the exponential decay.
Exponential decay, that would refer to the sum over all modes. Okay.
Oh,
As we'll see, in fact, in de Sitter, the decay is dictated by quasi-normal modes. So it's the lowest quasi-normal mode that's the most relevant.
In a flat space also it was sum.
In the flat space, it wasn't the quasi-normal modes. Okay, it was. Yeah, the quasi-normal modes don't capture the late time decay in flat space. In flat space, they give you an intermediate decay, and then at late time, it transitions to power law. Okay, and this is to do with the branch cut in the green function. Okay. But in de Sitter, they do give you the late time behavior. And so we want to know how does, so let's call this initial surface sigma. So how does, well, I won't write it down. We want to know, given some smooth initial data on sigma, how does the solution behave up here at the Cauchy horizon? And one comment on using the linear approximation here is that the linear approximation is going to be better when strong cosmic censorship is violated. If strong cosmic censorship is violated, then things are smoother at the Cauchy horizon. In other words, they're less singular, and so the linear approximation should be better. So if we use the linear...
I didn't get that. Sorry.
So strong cosmic censorship says basically things should blow up here. So if strong cosmic censorship is violated, then things don't blow up here, which means the linear approximation is better. So if we use the linear approximation and we find a violation of strong cosmic censorship, the linear approximation is more trustworthy. So it's self-consistent, the point I'm making.
I'm sorry,
Yeah.
just to get orientation for
Yeah.
de Sitter black holes. I've heard that there's a biggest size short shield black hole.
Yes, yes.
And what was the Penrose diagram for when you approach that?
So in that limit, the geometry degenerates. So this is called the Narii space-time. Yeah. So in that,
Which there's H minus
that's
C
rough.
plus.
No, that would be when this and this coincide. Okay, I'm not going to discuss that limit in these lectures. Okay.
The cosmological horizon and black hole.
Yeah.
So what does the diagram look like?
In that for the Schwarzschild case, in that limit, the geometry degenerates to a product of two-dimensional de Sitter with a two-sphere. You have to take a limit and do some changes of coordinates to see that. But yeah, it's called the Narii spacetime. Okay, so how are we going to study this? So we're going to set this up as a characteristic initial value problem. So what does that mean?
I'm really sorry, but
Yeah.
I'm still trying to process what you said about
Yeah.
the violation of cosmic censorship. I mean, if cosmic censorship is violated or the strong form, and there's a singularity on the Cauchy.
No, there won't be. If it's violated, so if it's violated, there won't be a singularity. Okay, so the conjecture says there will be a singularity. So if it's violated, then there won't be a singularity.
Then I have to ask my remedial question and tell me later, which is, I thought cosmic censorship was that all singularities are hidden behind.
No, that's weak cosmic censorship. So in lecture 0, well,
I'm sorry.
yeah. So the point is that they're logically independent, weak and strong cosmic censorship. Okay.
And you just once,
Yeah.
what is strong cosmic censorship?
It's the statement that if you have a Cauchy horizon, then when you perturb the black hole, that Cauchy horizon should be unstable. It should become singular in some sense. So, okay, yeah. Okay. So now I'm just going to draw the black hole exterior here. So this is the past cosmological horizon, past event horizon. So when I say I'm going to formulate this as a characteristic initial value problem, it means I'm going to look at linear perturbations coming from initial data, which is specified on null surfaces. And the null surfaces I'm going to choose are this and this. So my initial data is going to consist of a wave packet here, and a wave packet here. Okay, so I'm going to set up that as initial data and evolve it, and then ask what happens up there. So that's the goal. So we have smooth wave packets. On this union of null surfaces. Okay, so to explain how we do this, I need to go through some slightly boring material of just how we set up coordinates on Rice-Nordstrom. So the metric in the static coordinates that's the Rice-Nordstrom de Sitter metric. So this function here has 3 roots, which I'll call R minus, R plus, and RC, and these correspond to the Cauchy horizon, the event horizon, and the cosmological horizon. If I plot my function f, you can see that. Looks like this, so that's R minus, R plus, RC. Obviously, there's some restriction on the parameters m and q, which are the mass and the charge, in order to have these 3 roots. But
So these are Schwarzschild-like what?
yes. Yeah. So now we want to construct coordinates. So these coordinates are valid in region, I'll call that region 1, like region 2. These are valid in region 1. So to go into region 2, we need to define some new coordinates. The usual way. So starting in region 1, we can define a tortoise coordinate as follows. Okay, that defines R star up to a constant. I'll fix the constant by just putting some value at the lower end of the integral here. And this ranges from minus infinity to infinity. So it's minus infinity at the event horizon, it's plus infinity at the cosmological horizon. Having defined R star, we then introduce some retarded, advanced and retarded coordinates u and v. Call those equation star. And then we can define some ingoing coordinates v r theta phi, so that the metric in these coordinates looks looks like this. Okay, and these ingoing coordinates now cover regions 1 and 2. Okay, so there's no funny business at the event horizon in these coordinates, so they let you extend into region 2. So I'm sure you've all seen this before. So if we look at how these coordinates look on the Penrose diagram, then lines of constant v look like this. Okay, so they're just ingoing radial null geodesics, and the coordinate v increases in that direction. Okay, so the Cauchy...
Just one question.
Yeah.
Shall I ask you, is the fact you're in 4 dimensions going to be important for anything you say, or could you just do this in all dimensions?
At the moment, everything I say could be in any number of dimensions. Okay, yeah, the 4-dimensionality will only come in when I start giving some details a bit later on. Yes. And in fact, I should say, all of this formalism I'm now setting up is going to be used again in the ADS case. It's going to be exactly the same, so I'm not going to repeat it. Okay, so just to emphasize, in this region up here, the black hole interior, the Cauchy horizon is at infinite v. Okay. We can define the surface gravity of the event horizon, which I call kappa plus, which is half the derivative of f evaluated at the event horizon. Okay. Once we've defined the surface gravity, we can introduce Kruskal-like coordinates, which I'll call u plus is minus e to the minus kappa plus times little u, v plus is e to the kappa plus times little v. And these coordinates then let us extend into the other regions that we drew. So we plot u plus v plus his region 1 we started in. These coordinates also let us go into region 2, but they also let us go into these other regions, the white hole region and the other asymptotic region, as I'm sure everyone has seen when looking at the Schwarzschild solution, for example. So it's exactly the same here for Rice-Nordstrom de Sitter. So this would be the event horizon, and so on. Once we're in this region 2, it's going to be useful to be able to work with this outgoing coordinate little u. So we can define, remember little u at the moment is only defined in region 1. We can now give it a definition in region 2. So we define little u by the equation u plus big U is plus e to the minus kappa plus u. Okay, so that's now defined what little u is in region 2. Little v was already defined in region 2 because we used it to extend the metric into region 2. And we can also use this equation.
So is u basically the ingoing point from the other side?
Yeah, I'll draw a picture. So lines of constant u look like this. But an important thing to note is that u increases in that direction in region 1 and it increases in that direction in region 2. Okay. So this line here is u equals infinity. And that's the event horizon. That's the Cauchy horizon. Okay. Once we've defined, so then we can define outgoing coordinates. Little u are theta phi in region 2. Which will let us extend across the Cauchy horizon in region 2. So these extend. So the metric in these coordinates just looks like this. Okay, and so in these coordinates, the Cauchy horizon is just the surface r equals r minus. Yeah.
These coordinates also let us continue the metric behind the cosmological horizon?
No, we'd have to do it. So I won't discuss this, but you'd have to define a different set of Kruskal coordinates to go across the cosmological horizon, where instead of a kappa plus, you'd have a kappa c, where kappa c is the surface gravity of the cosmological horizon, possibly with some signs adjusted as well. Okay, then the final point is that having defined little u and little v in region 2, we can now define t and r star in region 2 by these equations. Okay, so then we've reintroduced the static coordinates in region 2, and you can see the metric takes the static form in those coordinates. So in terms of how does R star behave in region 2, surfaces of constant R star look like this. So they're space-like surfaces. So in region 2, R star is a time coordinate. Up here, R star is equal to plus infinity. Down here, R star is minus infinity. Okay. So, almost done with the coordinates. Final thing we need to discuss is the surface gravity of the Cauchy horizon. So, for example, using this, you can calculate the surface gravity of the Cauchy horizon. I'll call that kappa minus. So that's just given by half the magnitude of the derivative of f at r minus. And there's an interesting and important fact that kappa minus is always bigger than kappa plus. Okay, and this is going to be important later on. So at this stage, it's just an observation.
Would that be true for only the allowed values of m and q square?
Would it be true for?
Mass and the charge.
Would what be true?
This inequality.
This inequality is true for any Rice-Nordstrom de Sitter. Okay, yeah.
Is that true? Is it true in flat space as well?
Yes, I think so. Yeah.
But this surface gravity defined at the Cauchy horizon, that wouldn't enter any law of black hole mechanics.
No, the standard laws of black hole mechanics involve kappa plus.
Kappa plus.
Yeah. Well, in fact, in de Sitter they also involve kappa c. So there's the first law of black hole mechanics in de Sitter is, it was worked out by Gibbons and Hawking, and it needs both horizons. Okay, so finally we can define cross-scale, another set of cross-scale coordinates near the Cauchy horizon, which I'll call u minus. And so in these coordinates, region 2 is down here, and these three other regions all lie beyond the Cauchy horizon. Okay, so this is Cauchy horizon right, Cauchy horizon left. Okay, so similarly you can define a surface gravity for the cosmological horizon, you can define cross-scale coordinates for the cosmological horizon, but I won't bother with that. So the final comment here is about the extremal limit, which we're going to be discussing later on. So by extremal here, I need to say what I mean. What I mean is that r plus minus r minus is going to 0, which means it's equivalent to the statement that kappa plus or minus are both going to 0. Okay.
In that case, the Penrose diagram changes, right, to a time-like singularity.
Yeah, I'm never actually going to look at the extremal case. I'm going to look at black holes which are close to extremal, or a finite neighbourhood of extremality. Okay, good. So let's now move on to discussing the actual problem we're interested in, which is the scattering problem. So remember, we've set this up as a characteristic initial value problem. We've got wave packets coming in, and we want to understand how they behave at the Cauchy horizon. So this was first discussed in the asymptotically flat case long ago by Chandrasekhar and Hartle, 82. And so we're basically following their method. So let's look at, for concreteness, let's look at a scalar field with some mass. So we're going to consider solutions phi of this equation, which we can get by superposing mode solutions. So a mode solution has the form just So definite frequency times some radial function times a spherical harmonic. Okay, so if we plug this into the Klein-Gordon equation,
Where are you solving now? Which region?
1 or 2. So we can, remember I told you we can define the static coordinates in either region. So in practice, yeah, we're going to do this in both regions. Yeah. So at the moment I'm not going to tell you which region I'm talking about. Plug this into the equation and you get an effective Schrödinger equation, oops, with respect to the torus coordinate r with some effective potential V and eigenvalue omega. So V I'm not going to write down. It depends on the harmonic L. The only thing I'm going to need to tell you about V is that this vanishes exponentially as R star goes to plus or minus infinity in region 1 or in region 2. And just coming back to something you asked earlier, Shiraz, is that this is the difference with the asymptotically flat case. So in region 1, this would not vanish exponentially in the asymptotically flat case. Yeah.
So in this region billiard coordinates, the outer horizon of the black hole and the cosmological horizon get mapped to the whole line. So in this R star coordinates, and I've been thinking the region behind the horizon is inaccessible.
Yeah, so you have to think about that there are two sets of T and R star coordinates. T and R star are defined in region 1, where R star has an infinite range, and T and R star are also defined in region 2, where R star also has an infinite range. Okay.
And how are you going to match the two?
I'll match the two by using these other coordinate systems I've defined, which do extend
Why
across.
don't you just work in ingoing coordinates?
Because ingoing coordinates don't give us this nice effective potential. It's just the scattering problem looks nicer in the other coordinates. I mean, it's not a big deal. I mean, it's just, we know what's going to be smooth. So the point of the ingoing and outgoing coordinates is we can easily see whether something's smooth or not.
So this is vanishing exponentially in R star, right?
Yes, yeah.
And this statement is both true in de Sitter and anti-de Sitter.
Well, anti-de Sitter, I'd have to say in region 2, you'd now have a time like infinity. And then so R star actually in anti-de Sitter, I think, has a finite, I think that's right, I think it has a finite range. So it doesn't go to infinity in region 2.
But in region 1.
Sorry, I've said that wrong. In region 1, it has a finite range. Yeah, time like infinity is in region 1, and R star doesn't go to plus infinity in region 1.
ADS is a box.
Yeah, it goes to a finite.
It's a confining
Yeah. Yeah, so this is again different in ADS. In ADS, the potential would go to 0, I think, at some finite.
Okay, let me ask this question. In ADS, as you go towards the boundary, towards the non-boundary, let's say, towards the boundary where the field theory lives.
Yeah, time-like boundary, yeah.
Time-like boundary. And then what is the behavior of the potential? Is it still going to be exponential?
No, because R star is not going to infinity anymore. It's going to just some finite number. And I think it depends on the mass actually. But if the mass is big enough, it's going to 0. But if the mass is 0, it may not go to 0. But you know what to do in ADS, right? You impose Dirichlet boundary conditions or Neumann or whatever, depending on the mass. So anyway, I'll discuss this in more detail in lecture 3. Yeah. Yeah.
So how does this PLR look like? I mean,
How does what look like?
PL, the potential.
Oh, typically it just looks like this. So in region 1 it looks like this. Region 2 I can't remember, but it's probably similar. Okay, so let's consider, since we're interested mainly in the Cauchy horizon, let's start in region 2. Yeah.
So just from the naive expectation from ADS, it would seem that the effective potential in region 1 that would be unbounded from below sufficiently.
Yeah, you mean for negative mu squared?
Yeah.
Possibly, but whatever it is, we know what the right boundary conditions are, so it's not going to be an issue, as long as we're above the BF band.
Check one completely. About this power law decay in flat space, would there be power law decay for gravitational fluctuations around the sun as well then?
Yes.
It's just anything that has a mass.
Yeah. It's also true in odd dimensional Minkowski space.
I think
Yeah.
it's the difference between the delta function and the...
Yeah.
Yeah.
Yeah, the question is whether the green function is supported on the light cone or inside the light cone. Yeah.
So kinematical.
Yeah. Well, it's kinematical in Minkowski, but for in even dimensional case, it's
very little.
yeah. Yeah, it's basically in even dimensional Minkowski space, you have the strong Huygens principle, which says that if you wait long enough, everything has decayed inside the light cone. But that's only for exact Minkowski in even dimensions. Okay, anyway, that's a bit of a digression. Let's solve this equation. So in region 2, we can define two linearly independent solutions. This is just a scattering problem now. Let me define, can you see if I write down here?
Subra, can you see at the bottom of the board?
Yes, we can see.
You can see? Okay, good. All right, so let me define R.
We can see because we can see on his.
Okay, I'm going to I define two solutions by their behavior as R star goes to minus infinity, which is the, if I draw region 2 again, it's these two regions here. Okay, so that gives me two solutions going like, so the potential vanishes as R star goes to minus infinity, so I get two solutions going as e to the I omega R star and e to the minus I omega R star. I should emphasize at this stage omega is real, so everything, the frequency is real here. So I'll call them R out and R in because one of them is smooth on the left horizon, the other is smooth on the right horizon. Or let me say it slightly differently. So these are just solutions of the radial equation. If I plug back into here, I get solutions phi, which I'll call phi out plus and phi in plus. And these are going to be smooth on this thing here, the left component of the inner horizon. And these are going to be smooth on HR plus. And the way to see that is to convert to the Eddington-Finkelstein coordinates that I defined previously. You can see here, if I multiply this by e to the minus I omega t, it gives me something that goes like e to the minus I omega u, which means it's smooth along here because lines of constant u look like this. Okay, similarly for the other one. Okay, so these...
And there's no mode that's smooth on both.
No, the mode solutions themselves are not smooth on both, but by superposing them, I can build wave packets which are. So phi out plus is going to be a basis for solutions of the form like this. So we have some wave packet coming from here. There's nothing here, and this wave packet scatters to produce a wave packet here and here. Okay, so this is region 2. And similarly, phi in plus is a basis for solutions where we have a wave packet coming in from here, which scatters, and there's nothing here.
So it literally has zero support.
That's right, yeah. So we're just building a Gaussian wave packet here, and if we build a Gaussian wave packet there, it will vanish along there.
I thought your initial value surface was the null boundary, past null boundary of 1
Yeah,
and,
so
and 2.
that's right, yeah. So
You were,
yeah, so I'm going to come to that. But at the moment, I'm just going to think about solving the scattering problem in region 2, and then I'm going to match it to a solution of the scattering problem in region 1 to actually solve the problem I'm interested in. So if you like, this wave packet here is going to be determined by what happens in region 1. Okay, but I'm going to, for the moment, I'm going to ignore that and just focus on region 2, just to explain how the behavior of these wave packets is related to the behavior at the Cauchy horizon.
And Gaussian is good enough because that boundary is at infinity.
Yeah. 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 Okay, good. Right, so now we can write down a solution in region 2. I mean, but this is all the same kind of stuff you would do when you discuss Hawking radiation, for example. It's all the same kind of ideas. So again, in region 2, the black hole interior, I'm just going to write down a solution as a superposition of these mode solutions with some coefficients, which I call z of omega and z tilde of omega. Okay, that's clearly a solution because it's a superposition of solutions. What does it describe? Well, we're just superposing these wave packets. So it's going to describe something with a wave packet here and a wave packet here, which scatter to produce wave packets here and here. And this z and this z tilde are just the Fourier transform of the wave packets down here. So this is an outgoing wave packet. And if I were to introduce the Eddington-Finkelstein U coordinate, that wave packet would just look like this. It would be z of omega e to the minus I omega u on this surface. So z is literally the Fourier transform of the wave packet on this surface. And similarly, this is an ingoing wave packet. And it would have Fourier transform z tilde. So that's e to the minus I omega v. Okay. I should emphasize, as I said to Gautam earlier, this is not really something we're free to prescribe. This is really determined by solving the scattering problem outside the black hole. But for the moment, let's just pretend this is something we are free to prescribe and see where we get. This is a solution. We know how the solution relates to the initial data. So z and z tilde were determined by our initial data. So now we just need to figure out how the solution behaves up here. And we can see how smooth it is at the Cauchy horizon. So to do that, we need to introduce a new basis near the Cauchy horizon. So we can define an alternative basis, R out minus, which goes like e to the I omega r star, R in minus e to the minus I omega r star. But now as r star goes to plus infinity, which is towards the Cauchy horizon. Okay. So from these I can build modes called phi out minus and phi in minus. And so for example, phi out minus is going to be a basis for solutions which look like this. There's going to be an outgoing wave packet up here. It's going to be 0 along here, and there's going to be some ingoing wave packets down here. Okay, and similarly for the other one, we're going to have a wave packet here, 0 here, wave packet. Okay. So what we need to do to figure out how this solution behaves is we need to rewrite the basis with understood behavior down here in terms of the basis with behavior we understand up here. Okay. So we need to relate these modes to these modes. So we need to relate the plus basis to the minus basis. In other words, we need to solve the scattering problem. And so we introduce some coefficients. A, maybe I'm running out of space here, let's go over here. So we'll define scattering coefficients so we write the plus basis in terms of the minus basis. Okay, so that's just defining these coefficients, A, B, A tilde, B tilde, in this basis transformation.
The B fellows come with the complex conjugate of R in minus, etc.
No. I'm defining omega to be real, so this is always for any, so I'm never taking any complex conjugates or anything. If I want to look at negative frequency, I just take omega to be negative. Okay.
fellows don't.
Well,
fix the
Bogdanov coefficients you introduce when you've got mixing between positive and negative frequency. We don't have that here. There's no mixing because we're in a static space-time. Okay.
Oh, yes.
Yeah, everything has the same frequency. Okay. So, so now I can plug this into here, and I can decompose phi into an outgoing part near the Cauchy horizon plus an ingoing part. So just substitute this into here, so for at the level of the phi's. So the outgoing part, z of omega, a of omega, plus z tilde of omega, b tilde of omega, phi minus. Yep.
There is something in addition. In region 2, R star is the time-like coordinate, right?
Yes.
So there is mixing between positive and negative frequencies. I mean, these two guys are, so these are really Bogoliubov coefficients, aren't they? Because you're really
well,
omega R star equals minus omega R
I
star.
mean, maybe a better way of saying is that in region 2, R star is a time-like coordinate, so omega is not really a frequency, it's more like a wave number or a momentum.
But it's always time-like.
Yeah.
It's not like you're mixing between the two.
Yeah, there's no mixing, because the symmetries are preserved. So that's yeah.
So when you were considering scattering,
Yeah.
I mean, you're supposed to use something like plane waves, not sine, cosine stuff, not standing wave kind of.
Yeah, I'm not using standing wave. Remember, these were defined in this way. This is just a plane wave.
Yeah, then somehow in your definition you're already taking care of that.
I mean, if you like, this is so maybe one way of thinking about it is the two modes here you can think of as one is the mode for positive omega and the other is a solution with negative omega. And so if you like, in that sense, yeah, if you like, you could take this. As long as we're working with real omega, you could define this to be the complex conjugate of that, and maybe that would, maybe that's what you were thinking of. Yeah. Yeah. But it's going to be kind of important because we're going to be doing some analytic continuations in a moment. It's important that we don't do that because it would make the analytic continuation a bit confusing when we let omega go complex. Okay.
Sorry, just to clarify, one more thing with what Shiraz said. So if I started with the mode that went like e to the minus I omega r star on the past,
yeah.
As I went to r star equals to plus infinity, which is the top horizons, that would convert into a combination of e to the plus I omega r star and e to the minus I omega r star.
Yeah. Yeah.
So in that sense, you start with positive frequency in the past and it goes into a combination of positive and negative frequency in the future. I mean, that is.
Well,
I just want to make sure I'm understanding this correctly. Yeah.
Yeah, that is true what you just said. That yeah, if you want to think of it that way, yeah, you can. But really, it's just saying something. It's a scattering problem, right? You have something coming from the left, and you get a transmitted part and a reflected part, and one is positive omega and one is negative omega.
Yeah.
Okay, so that's one part. The other part, I'll squeeze it underneath. Okay, so we've now written phi as we've decomposed it into a part, a superposition of the out modes. In other words, a superposition of these modes, which look like this, which is the outgoing part, and down here an ingoing part, which is a superposition of modes of this form. Right. So we've split the field into an outgoing wave packet and an ingoing wave packet at the Cauchy horizon. Now, if we look at this part, by definition, these modes phi out minus are smooth here. This is the part of the Cauchy horizon we're going to be most interested in. I should have emphasized this earlier, but I'm entirely going to be focused on this segment of Cauchy horizon, not this one. The reason is that this is basically universal, particularly this early time segment of the Cauchy horizon. For example, if you have a black hole formed in collapse, this is the thing you get, whereas this is very dependent on how you form the black hole details. So we're going to be focused on this section. So phi out is smooth at this right-hand component of the Cauchy horizon. And that's just because it's a superposition of these modes which are smoother. Okay. So on the other hand, phi in isn't smooth there. Okay, so the reason for that is that we have some tail, and it's this tail as we approach this edge here, which gives us some kind of non-smooth behavior, as we'll see.
I'm sorry, Harvey, could you draw the 4 modes on the board?
All 4.
If you don't mind.
That means I have to remember them now. Okay, so here we've got, so this would be phi in plus. This is phi out plus. This is, let's do in. Phi in minus. And phi out minus. Okay, or, well, more precisely, the in plus modes are a basis for wave packets of this form, more precise.
And now you said that phi out is smooth?
Yes.
Phi out?
Phi, this phi out here, which I've defined, is a superposition of the phi out minuses, which are these ones, okay, which are smooth up here. Okay.
Okay.
The individual modes are smooth up here.
Yes, yes.
Okay, so it's guaranteed that this is going to be smooth there.
Okay.
But here the individual modes are not smooth here. Sorry, the individual modes for the in modes, the individual in modes are not smooth here, but nevertheless I could superpose them to build a wave packet, which was, okay, but it's not clear whether the superposition I'm actually getting here is a wave packet of this form. And in fact it's not going to be a wave packet of this form, it's going to have some tail, which is going to make it non-smooth here. Okay. And there's an easy way to see that, actually. We can see that straight away, where the non-smoothness comes from. Shall I erase this?
Actually, it would help me a lot to have it on the board.
Okay. Let me erase this. I think we need a bigger...
Yeah, these were phi out, phi in terms of this language, that was this. Is that in plus? Is that plus doing something?
That's a plus. This is telling me that the notion of inness is defined at the plus, which is the event horizon. And here the notion of inness is defined at minus, which is the Cauchy horizon.
And what are there, should there be pluses and minuses here?
No, well, I could put them on, but then that would confuse. So this is a general solution, and I've split it into an outgoing part and an ingoing part. If I put, I mean, morally there are minuses here, but if I put them on there, it would confuse my notation with the notation I've used for individual mode solutions.
But just to understand, the out, phi out refers to some combination
of outgoing modes, yeah.
And therefore, in your notation, is it phi out, combination of the phi out plus and phi out minus?
No, so this is just the so these are the modes, right? So this is where all the space-time dependence is coming in. It's in here. So these modes are a basis for things of this form. Okay, the modes themselves would look like this. They'd be oscillating along here, and they'd actually be singular along here. Okay, but by superposing.
So that's phi out, and you take a particular superposition.
That's the Z.
Yeah, this is the Z. So the Z. Remember, the Z and the Z tilde were determined by initial data, which I've specified down here. Okay, so these are the profiles of my ingoing wave packets. So this is relating the ingoing wave packets here into outgoing wave packets. So these two things are giving me the profiles of these two wave packets up here. Okay, so that's what I've done. I've written these two wave packets in terms of these two wave packets.
Right, so you just took Z's as your data here and
Yes.
transformed it into up.
Exactly. That's all I've done. Yeah.
Yes.
So basically, sorry, just to
Yeah.
understand, so the phi out mode goes to A omega phi out minus plus A plus B omega phi in minus, and that's how you transform.
Yeah, I've just substituted this into here, basically. I've replaced R's by phis.
Okay,
Yeah.
now there's also R.
Yeah, so remember, phi is, so R is just the radial
radial part.
function. So I multiply that by
Okay.
by e to the minus I omega t and so on. Like, yeah. Yeah.
It confuses me how you put out and plus and minus.
Yeah.
Anyway, later.
Is this,
that's the confusing part for me also. This out and this plus and then this.
well, in a moment we're going to define another set of modes associated with the cosmological horizon. Yeah, but the trouble is there are too many things to define and not enough letters and symbols to define them all. Okay, so to explain why
Plus means early time and minus means the late time.
plus refers to R plus, which is the location of the event horizon. Minus refers to R minus, which is the location of the Cauchy horizon.
Yes.
Sorry.
So plus is initial data.
Minus
Minus is final.
Yeah, so plus, this is R plus, this is R minus.
R plus and R minus. Okay.
Yes. You should always
Yeah,
make your...
in terms of the potential, the same things to be drawn in terms of potentials. Left
Well,
stuff going.
I mean, I could call it, if I worked with if I worked with R star, then plus would be plus infinity and minus would be minus infinity.
This is the out and in part of the final solution.
That's right. Yeah. Right. Good. So okay. So let's see why is this thing not smooth? So we can.
At some stage, there was a sum over the partial waves that's implicit in.
Yeah, I've kind of suppressed my spherical harmonics, so I'm not going to.
The phi's themselves don't have the LM indices.
No, yeah, I'm suppressing all of that.
There's
In principle, Zs should have an L and an M on them as well, and phi's as well. But then my notation is just going to be horrible. So I'm.
So each of these phi's is a particular
Yeah.
partial wave.
Yeah. So each thing is defined as a product of a radial function with a spherical harmonic and e to the minus I omega t. So in principle, Z should also carry an LM index. So should phi. But I'm suppressing all of that because it won't matter, and it just complicates the notation, which is complicated enough. So let's see why is phi in not smooth. Let's evaluate this as R star goes to infinity. So as R star goes to infinity, in region 2, remember that's the same as V goes to infinity. So
But the question of whether it's smooth or not will depend on Z, won't it?
yes, yeah.
You've chosen Zs to be some Gaussians.
Well, I haven't told you much about the Z so far. I'm going to say a bit more about them in a moment. Yeah.
From your calculation, you were expecting the ratio will be phi out, right? On this side.
On which side?
Phi out.
So phi out is the smooth part. So the thing we're going to see a non-smoothness here, but the non-smoothness is actually coming from the ingoing stuff, okay, which is associated with phi in. Okay. So to see why phi in is not smooth, we just so it's the ingoing thing which is not smooth, and we just write that in terms of the Eddington-Finkelstein coordinate v. Okay, so I've just written this as R star goes to infinity, phi in just becomes e to the minus I omega v. V is the Eddington-Finkelstein coordinate, which tends to infinity in this direction. Okay, so lines of constant v look like that. Okay, the point is, e to the minus I omega v is not smooth up here. I'm going to have to erase this now. So if we convert to the cross-scale coordinates,
Because V is infinity.
because v is infinity, but if we convert to the cross-scale coordinates, we get this. The sum over omega, in principle, might make it smooth, and that's the question of whether it does or it doesn't. Okay, so we're going to have to understand that. Yeah, and the answer will be that it doesn't.
Depending on Z, right?
Yeah.
No, I mean, I thought if you start with some compact support object.
Well, we're going to discuss exactly that right now. Well, we've got to finish it in half an hour, well, half past. So we may not see it right now, but we will discuss that at some point, maybe at the start of the next lecture. Okay, but what we want to understand is the behaviour of this as v goes to infinity. Okay, this is a late time thing, and so there's of course a standard thing that we learn when we're studying this kind of thing in undergraduate courses. How to do this is we deform our contour of integration for omega into the complex plane. So we deform into the lower half plane. So this is the complex omega plane. So here's our initial contour, which is along the real axis, And we're now going to shift to a contour down here.
Oh, so the non-analyticities of this function are going to matter.
Yeah. So we're going to shift down a distance alpha. So in principle, we're closing this into a big rectangle like this, but the ends of the rectangle won't contribute because they decay at large omega. Okay. So if we think about so what does this mean?
And just to make sure, this is a contour in omega.
This is complex. Yeah, this is the omega integral. So this is the complex omega plane.
What did you do? You had to do an integration over omega, and then that was through a contour. Now you shifted the contour.
I'm shifting the contour down to here using the residue theorem. So I'm going to pick up contributions from any poles that might be between here and here.
And you're shifting it in the direction so that if you went to infinity, that would...
I want omega to have a negative imaginary part so that this thing decays at large V. Yeah, okay. And so the imaginary part on the new contour will be minus alpha.
And the lower thing you'll take all the way down to infinity?
No, I won't actually. I'm going to just keep it fixed. I mean, I can put it wherever I want. It will be the poles that dominate, but it doesn't really matter where I put it, as long as I push it past the leading pole. So I think I can probably erase that. Well, we'll see. So now, this integral over omega, this thing we're interested in, is going like an integral, the contribution from this new contour, which is going like e to the minus alpha v, okay, plus a contribution from any poles that we pick up with some coefficient, the residue of the pole, which will depend on the location of the pole times v. Okay, so omega pole is the frequency at which we have a pole. Okay.
You still have to do the contour integral over the lower horizon.
Yeah, that's this bit here. Okay, so this bit here is so there's some integral, but the integral is of this size. Okay.
And how about the two vertically cuts?
Okay, so in principle, so you should cut this off at some large frequency, and then evaluate the contribution from these, and then take the frequency to infinity, and you'll find that they decay. Okay. Actually, we didn't check that too carefully, but I think that large frequency limit is something you can understand from geometric optics in principle. And so it's for BTZ, we could check that. That was all fine. Okay, so we need to understand these poles. So alpha, if alpha, since it's below these poles, this is going to decay faster than this, and so it's this part which is going to dominate the large V behavior, which is the behavior we want. So where are these poles? So what you can show, so the thing we're looking at, the integrand, is this ZB plus Z tilde A tilde. Remember, Z and Z tilde come from our initial data. B and A tilde came from solving the scattering problem. What you can show is that the individual mode functions I've defined, when you analytically continue them in frequency, the mode functions have poles. And you can understand where those poles are. Okay, so those poles translate into poles in A tilde and B. Okay, so those poles.
The mode functions have poles in R star.
No, in omega. In omega, yeah.
There's bound states in the sketch.
Yeah.
No, the S matrix is a function of omega.
Yeah, A tilde might have poles, but just to understand, when you said the mode functions.
No, the mode functions are functions of T, R, and so on, and omega. But as a function of omega, they have poles at certain complex omega, which were basically these
But
values.
we're interested in the poles in B and A tilde.
Yeah, well, so the fact that the mode functions have poles translate into corresponding poles in B and A tilde. Okay. For real omega, that was how we defined them. But we're now going into the complex plane. We have to analytically continue them, and when we do that, it turns out that the mode functions develop poles at certain locations. It's not. These are not quite quasi-normal modes, actually.
Sorry, I had the same question. Isn't it still e to the minus I omega t for whatever omega you choose to look at?
But yes, but the there could be some coefficient in the expansion which depends on omega.
It's just the statement of the S matrix. It's the coefficients. You take e to the power omega t out here.
Yeah, that
And then it goes to
statement,
something.
that statement I understand.
That's its mode function. Right? Its mode function is something which on the left is e to the power omega t, and on the right is whatever it is.
Yeah.
Now the exponential part, the x dependence, the t dependence on omega t, but the coefficients are functions of omega.
Sure,
That's good to have poles.
Yeah. So the way you show this is you
That's
convert.
what he means by mode function.
You-
Mode function is these units.
Yeah. You convert this into an integral equation, and you solve the integral equation by iteration, and you see in that iteration process that the thing you're getting is developing poles at these
It's like in
locations.
quantum mechanics, so one-dimensional quantum
Well, it
mechanics.
is one-dimensional
Yeah.
quantum mechanics. Yeah.
Reflection on you get poles by your box.
Yeah. So A tilde turns out to have poles at negative integer multiples of kappa plus, and B has poles at negative integer multiples of kappa minus.
And to make this statement, you use that asymptotic form of the potential that went into it?
You need a bit more than that. So you really have to think about how you solve the Schrödinger equation, and you solve it by converting it into an integral equation, which you then solve by iteration, essentially. And so you're using the full form of the potential and the fact that it's an analytic function of R, which means that its dependence on R star is e to the minus kappa R star, and that's where these kappas are coming from, basically.
You at some point you had some intuitive explanation. The explanation was dependent on scattering off from the bound in the potential.
No, this is in region 2. He's not yet gone to
I've not gone to region 1.
all
no.
that.
But there is a potential in-
Structure in region
Yeah.
1 and region 2.
The potential has bound states, is that right?
No,
positive
no, not well. Certainly not in region 1. No, no.
I mean,
No, even in region 2, can
No, I don't think so.
trapping regions?
I don't think so.
that's not quite the origin of.
No, I mean the point is, I mean the thing that I mean that these are. I mean, if you look at this is determined entirely by properties of the event of the horizons by kappa plus and kappa minus. So it's not really the detailed structure of the potential that's
The
important.
asymptotics of the
It's the fact that the potential is a function of R, and R is a specific function of R star, which involves a kappa plus or a kappa minus.
But the structure of the potential in region 1 and region 2 in the asymptotic boundaries are the same.
Yeah, the exponential decay, with
Yes.
decay determined by the.
So we are solving the problem in region 2.
Mhm.
In region 2, as a Schrödinger equation problem, what is the phenomena that this is related to this one? What is the phenomena that you have these poles? Is it like some sort of the kind of things I was saying? Is this some interpretation of some bound states? If you calculate this matrix in this region,
I don't think it is bound states. I mean, well, I haven't seen a discussion of it in those terms.
It seems, I mean, you should go on, but it seems more like the underlying potential to begin with is a function of R. You convert R to R star.
Yes,
And there's a kappa plus or minus.
exactly.
And
That's
so
exact.
that
That's
decay
exact. It's exactly where it
seems
comes
to
from.
be-
Yeah.
seems to
Yeah.
be what it is.
So
Yeah.
if I could just add something which might help answer the previous question, there's a potential which you can expand in a power series in R, which goes like e to the kappa plus R star.
Mm-hmm.
And so when you solve the Schrödinger equation just with the Green's function,
That's-
the Green's function has an e to the I omega. And
Exactly.
you integrate it and you get these poles. So
Yeah,
where these poles
that's exactly right. Yeah, that's exactly what happens. Yeah.
But it's a very generic feature for problems of this structure that poles are related to bound states in some language.
Yeah.
I suspect it would be true here as well. Or
Um,
maybe the asymptotics is so different.
Yeah.
I'm not sure.
Yeah. Anyway, the poles are there. We can. In fact, when you look at BTZ, you can see all of this analytically. In BTZ, the mode functions are all hypergeometrics, and you can see the poles very simply. So that means, so we have these poles in A tilde and B. So let's understand what their contribution is to this. So we need their residues. So the residue from the B poles goes like minus V minus, so I'm just using this thing here, just plugging these values of omega into this. So it gives us n kappa minus over kappa minus, so the kappa minuses cancel, and that's minus V minus to the n. Remember the Cauchy horizon is at V minus equal to 0, n is an integer, so this is smooth. Okay, so these poles, although they're there, they're actually they give us something that's smooth at the Cauchy horizon. So they're not actually relevant.
So A and B poles are in
No, I'm only looking at the poles in the lower half plane here, so which is why it's minus I n kappa plus, both cases. Because only the poles in the lower half plane are relevant here. There are also poles in the upper half plane, but we don't care.
Because kappa minus was negative to begin with.
No, it wasn't. I defined it with a modulus sign.
Okay, kappa minus was different.
Yeah. Also, want to correct something.
Yeah.
Real poles in the scattering problem are related to real bound states.
Right. Okay.
These are complex poles.
Real poles do actually come up, and they have an interesting interpretation, which we can maybe discuss later.
So these are like more like resonances.
Yeah. Yeah. So there are real poles, and they have caused confusion. If we look at the other ones, the A tilde poles.
Reinverse states of the pendulum.
What?
I think these are like the reinverse states of the pendulum.
You're more educated. It's something that decays.
In the scattering medium, there's stuff, which looks like has a quantization of the resistance.
Okay, so the pole so let's look at these other poles, the A tilde poles. So now we've got a different exponent up here. And I've also written the Z tilde coefficient coming from here, in here, evaluated at the pole. And now you can see this thing is not smooth because it's got a ratio of kappa plus over kappa minus. And remember I told you that kappa minus is bigger than kappa plus. So these are, it seems, not smooth. So if we have 5 minutes, then I can answer the question that was asked earlier about compactly supported data. So if we take a toy problem, we can take compactly supported data on...
Sorry, so far you've answered the question that one of these modes grows like V.
This is, yeah, the point is it's not the growth, it's the fact that it's a non-integer power, so it's not smooth. Okay, so this is a non-smooth contribution to the field. So for n equals 1, this is not differentiable at the Cauchy horizon. So its gradient will blow up.
Okay. And just to understand, I mean, the Cauchy horizon per se, was that V equal to 0?
That's equal to 0, yeah. So this is a not, so kappa minus is bigger than kappa plus. So if I just look at the n equals 1 term here, this is a power of V which is less than 1, so the gradient of this is going to blow up. Okay.
So just one more question. It's important it's a non-integer power that is smaller than 1, right? So when you calculate the stress tensor, you get the divergence.
That's right, yeah.
If it's non-integer power larger than 1, you wouldn't care, right?
It would be non-smooth, but it would have a finite stress tensor. Yeah. So if you just leave me, let me just go. I've got 2 minutes, so let me do this. So take them to be compactly supported, these two ingoing wave packets. What does that give us? Compact support tells us that Z and Z tilde are entire functions, okay, of omega, which means they have no poles. So these are the only poles, in other words. Okay, so therefore we can deduce that in this case the leading n equals 1 term dominates, so we get kappa plus over kappa minus, and Z tilde of minus I kappa plus near the Cauchy horizon.
Wait, so you said that Z is compactly supported in time?
In time, yes.
Means
So these are,
Fourier space is an entire function?
yeah.
Isn't it non-analytic in time if it's compactly supported?
No, it's analytic in omega. Sorry, yeah, it's analytic in omega. If it's compactly supported in time, then it's an entire function of omega.
Yes, but if it's really compactly supported, it's not an analytic function.
I don't care. I mean, I don't want it to be analytic in time.
You do?
I don't. No. I certainly do not. No.
Okay,
No.
but I thought that if you have a non-analyticity in time,
Yeah.
that usually leads to like power law decays, not exponential decays. If I take a step function, I
Yeah.
get a sine omega by omega,
Yeah, which is an
which
entire.
doesn't look entire to me, does it?
Sine omega.
Sine omega by omega.
Yeah, that's an entire function.
Thank you.
Yeah.
It's compact in time.
It's compact. This is time. This is time. It's compact in time.
Compact
Yeah.
in time.
Yeah.
Then
So it
you
means
say
it's.
that means I should have an education, but anyway,
Yeah.
this means it's actually.
It's very simple. It just means you can. The Fourier integral is as convergent as you like, and you can make omega complex, and there are no problems.
Fair enough. I see.
Yeah.
And but it will die slowly at omega equals infinity.
Yeah, but I mean, it dies fast enough for it not to be a problem. So one more sentence. So the observation is kappa minus is greater than kappa plus. Tells us then that phi in is not C1 at the Cauchy horizon. So as was mentioned earlier, that means the stress tensor diverges there. And we have the Cauchy horizon instability.
And just to understand, it's that kappa minus is bigger than kappa plus.
Yeah, yeah. So this was the observation I mentioned earlier. Okay, so this was a toy problem. What?
It went too fast for me.
Yeah.
So Z was compact and
Is it both of
Z was
both of these are compactly supported?
so, yes. So Z tilde k was entire.
That means they're both entire functions. Z and Z tilde are
Fine.
entire.
And therefore V times that was.
So therefore, there are no poles coming from Z and Z tilde in this term, in this expansion. So the only poles are the ones coming from A tilde and B, which are the ones we've just discussed here.
Yes.
Okay.
So your analysis is now
Yeah.
accurate.
So there are no other poles to worry about, and it means that these poles here dominate, and you get this result. So this looks very nice. This seems to be giving us the Cauchy horizon instability.
Yeah, just multiplied by Z at that pole value.
Yeah.
Something.
Yeah, exactly. Now, but why did I call?
So in constructing the stress tensor, you do derivative with respect to the Kruskal B.
Yeah,
And,
yeah. For
Kruskal
example,
B,
yeah,
right?
yeah. So that will blow up. So why was this only a toy problem? It was only a toy problem because, well, I mean, actually these are not compactly supported. So in particular, this wave packet here is determined by solving the scattering problem in the exterior. When we solve the scattering problem in the exterior, what we will find is that this is 0. So this pole is actually not there. So we're going to find that this apparent pole is actually, in the toy problem, is actually not real.
The value of Z at the value of the polynomial.
Yeah, so this, the Z tilde evaluated, at any of these, Z tilde analytically continuing in the complex plane vanishes at all of these. Yeah.
I see, very interesting.
So we'll see that next time, I guess. Well, I'll
so, but then just to jump ahead,
Yeah.
will that therefore mean that you don't have an instability?
no, because there will be extra poles in Z and Z tilde because it's no longer compactly supported.
So
And well, the extra poles will come from quasi-normal modes in the exterior. Okay. Sorry? They're not so, well. There'll be extra poles in Z tilde coming from the fact that this is not compactly supported in time up here, which when we go into the complex plane will give us new poles, which in fact the decay in time is dictated by quasi-normal modes out here. So those poles will actually be located at the quasi-normal modes of the black hole.
And how would it be dominant?
Essentially, the problem was coming from late time behavior in region 1.
Yeah.
So if it is compactly supported, you are not going into that region.
No,
That
exactly.
That was giving the problem.
Yeah, that's
Therefore, this is not the right toy.
that's why this is only that's why I called it a toy problem. Yeah.
So the poles that come from Z tilde would be dominant compared to the other poles in this expansion.
Well, the other poles are these just give you smooth things, and these are not really there because they get multiplied by zeros. Okay.
But suppose that n equal to 2.
Okay, but there will also be zeros at n equals 2. All of those, there are zeros at all of those. Yeah. Yeah.
But those would be, even in the toy problem, those could cause instabilities in
Oh yeah, in the toy problem they're definitely there, but in the real problem they won't be.
No, but the n equals 2, 3 and higher modes, they wouldn't.
They're not smooth. They won't have divergent stress tensor, but
yeah,
they're not
but
smooth.
I mean, provided that k plus it's in k plus over k minus is bigger than 1.
Yeah.
They won't cause any problem in
They
the
won't. Yeah, it depends what you mean by a problem.
I mean, the stress tensor wouldn't diverge.
The stress tensor, yeah, the stress tensor won't diverge, but they won't be smooth. Yeah, yeah, yeah.
So physically,
Go ahead, Suraj.
yes, right. Yeah, so the question was physically you could think of an observer who went very close to the horizon and then sent in data from there. In which case the toy problem would be the real problem, right, for such an observer. I mean, not someone who's sending in data asymptotically, but someone who went very close to the horizon and then threw in stuff.
Well, I mean, if that person
Is
is,
that-
I mean, if that person is the only person in the universe, I mean, but in practice, that person, when they're outside the black hole, is going to be moving and emitting gravitational waves, and those waves will hang around forever, and so there's always going to be some late time stuff in the region 1, which is going to fall in at late time.
Yeah, no, I understand. I'm just trying to argue that you might have naively thought that there was a problem with proving cosmic censorship because of what you just said. There's this decay outside, which
Yeah.
causes Z tilde to be 0.
Yeah.
But I was just saying, if you thought of the problem where someone was really setting initial data where you set it at the outer horizons,
Yeah.
which is not an unphysical thing to do, then you would imagine that you would get a singularity, right? If you
Well, I mean, I agree. If you can really set this up, then you do get a singularity. But I would say it is an unphysical thing to do if there is a region 1, because if there is a region 1, there will be stuff that just hangs around for a long time in region 1 and decays exponentially.
Just one thing about it.
Yeah.
Sorry, let me just ask.
I should just ask, how seriously are we going to get kicked out of this room at 11:30?
What's at 11:30? Oh, it looks like nothing, right? Let's just keep going till somebody comes. I'll just go ahead and look.
You should ask, but just to, so physically the point is that if you include region 1, the quasi-normal modes from there ring down on some exponential decay.
Yeah, well, let me just, I'll just say a little bit more. There is a danger if we keep going, I'll run out of lectures, but we'll just go very slowly in lecture 3. Yeah, okay, well, you tell me when to stop then.
Okay, no, I didn't about the lectures. So
Yeah.
if you're happy to stop, we could stop. I recommend you keep going with the discussion.
Yeah, well, I mean, the discussion is asking what happens next, which is which is the real problem. Let me just say, write something down.
Actually, then in that case, if you're going to the real, just to ask you about
Yeah.
what you already said, if you take the toy problem anyway, there's more to do just from saying there's an instability to saying there's a singularity, right?
Yeah, because this is linear, but if you have a divergence in the stress tensor in the linear theory, then you would expect nonlinearities to cause a... Yeah, and so in the asymptotically flat case, there's now a lot of evidence that is indeed true, and so that when you go from linear to nonlinear, the nonlinearities behave as you would naively expect, and you do indeed get a singularity at the Cauchy horizon. Okay.
So suppose we were doing asymptotically flat and just region 2.
Yeah, this is all exactly the same.
All the same.
Yeah, this is exactly what Chandrasekhar and Hartle did.
Right.
Yeah.
But that jump, going from the instability to the singularity must be pretty non-trivial, just in terms of, because you have to analyze the full.
Oh yeah, I mean that's why. Well, it was first discussed in a toy model by Poisson and Israel, where instead of a scalar field, they put in null dust, which is something that's tractable analytically, and so they could handle the nonlinearities. But the real case where you couple a scalar field to say Einstein-Maxwell theory at the nonlinear level is something that's been understood by Mihalis de Fermos is the pioneer on this, and so it's rigorous PDE analysis. It's hard work.
Coming back to Z tilde, so it is very important that for the potential in region 1 to decay exponentially so that you get the Z tilde at the Z residues to be 0 in this toy problem to begin with.
Well, he said it's the same. It's the same for flat space. It's the same for everything.
So therefore, it is not important that you had an exponential follow, because in flat space you said it's not exponential.
No, the point is that what's happening is we've seen that these poles came from the analyticity properties of the mode functions. Okay.
Yes, yes.
Now, it turns out, well, so there are going to be similar analyticity properties for the mode functions defined in region 1.
Yes.
And it turns out that those analyticity properties are what give you that this is going to be 0.
And
Okay.
those analytic properties depends on the form of the potential in region 1.
Well, the fact that there's a 0 at kappa plus depends on the behavior near the horizon, not on the behavior near infinity. Okay.
Right. So if you start with ADS, then will you have the similar?
Yeah, it's the same in ADS.
Okay. So
Yeah.
even in ADS, you need to go to length time to see anything diverging.
Yeah, even in this would all be true in ADS as well. Yeah. So in the real problem then, Z tilde would be determined by solving the scattering problem in region 1. So here's region 1. In region 1, we now have the past event horizon and the past cosmological horizon, and we're going to put wave packets on these, which I'm going to call x of omega and x tilde of omega. And they're going to determine what happens up here, which is this z tilde. Okay, there'll also be something here. So what you find when you solve the scattering problem is that the analyticity properties of the mode functions in region 1 guarantee that z tilde has zeros at these points, as I said. So these above poles are unphysical. But you also find that z tilde of omega has poles at quasi-normal frequencies. Okay, and this was all pointed out by Meller and Moss, 1990.
So you had these a and b function having poles with very simple values. Is there some reason to have expected that? Why would these values be different?
It's simply that the mode functions have poles at those values, and that translates. And since the a's and the b's.
Why did the mode functions?
So this is what we discussed earlier. That the clear explanation came in across the ether, which is that we've got e to the minus I omega r star. And we've got a potential which is, we could write, it's an analytic function of r, but r is basically e to the kappa, well, r minus r plus is going like this. So when we solve for the mode functions by iteration with a green function, we end up with integrals like the r star e to the minus I omega r star e to the kappa r star to some power. So the potential involves powers of r minus r plus. It's an analytic function of r minus r plus, so it's powers of this. So when we solve by iteration using a green function, the green function has r star dependence roughly like this. And when we evaluate this integral, you see there's a pole at omega is minus I n kappa plus. That's the rough reason. So it's, what is it, Volterra integral. So
that part there was you said the potential went exponentially with r star.
Yeah.
So this should be a property of quantum mechanics, that if I take potential that is exponential with r star, and I compute something.
So if the potential is a sum of exponentials of r star, yeah, or just I guess
x.
Yeah, or just one potential, yeah. So then you'd expect to see poles. Yeah, I guess it would be similar. Yeah, at locations determined by the exponent in that potential.
Right. It's just because when you make things complex, the wave thing becomes complex.
Yeah.
One beats the other.
Yeah, exactly. Yeah.
Right.
Yeah.
I see.
So what's the plan? Are we going there?
Well, yeah, you tell me. I mean.
I'm also going ahead for a very selfish reason that I'm out of town tomorrow.
Well,
but then, no,
that's good. I mean, if you don't.
I don't mind. Okay.
So this part of the mathematics is rather different in ADS. Is that
No, it's not actually. Well, in ADS, in region 1, you wouldn't, I guess there would be an issue with r star going to plus infinity because the boundary is different, but you know how to deal with that in ADS. It's just the Dirichlet or Neumann boundary conditions. But apart from that, near the horizons, this is still true. And so you still get poles for this reason, for the mode functions defined near the horizons.
It is related to behavior of the potential near the horizon.
Yeah, so for example, if I'm looking at the modes R in plus and R out plus, then these are defined by their behavior near R equals R plus. And so it's natural then to expand the potential in terms of r minus r plus, which is the same as expanding as e to the kappa plus r star. And when you do that, you pick up these poles, which means that r in plus and r out plus have poles at these locations. If you do it with the minuses, then you do put minuses here, and you'd get poles at with the minus here. So the other set of mode functions has poles at locations related to kappa minus. Okay. So the mode function defined by boundary conditions at r plus will have poles at negative integer multiples of kappa plus, and the mode functions defined by their behavior at r minus would have poles at integer multiples of kappa minus. Okay,
for real omega is mod a squared plus mod b squared equal to 1 or something?
Yes, yeah.
So this can only, so then this would be inconsistent with having a real pole.
You can have the real pole at omega equal to 0.
Omega equals 0
because then in and out become degenerate, and that's basically the reason. Yeah, there is an interesting story about those real poles, which I'm not going to discuss. I can tell you now, actually, which is that so it turns out that if you do asymptotically flat Rice to Nordstrom, those real poles are absent. And that translates into the fact that when you solve this problem in region 2, let's go to region 2. So this is for Rice to Nordstrom with lambda equal to 0. In region 2, if you solve this with compactly supported data, then the solution, it turns out, always vanishes here. Okay? It's always 0 on that bifurcation surface. Which is rather surprising, right? And that's a direct consequence of the absence of the pole at omega equal to 0. So this was proved recently by Kahler and Schlappentop-Rothman, who are mathematicians. But if you include a cosmological constant, then the pole at omega 0 is there, and now the solution is non-zero up here.
So Shiraz, I think you need a squared minus b squared equal to 1.
It's something like that. I mean,
a squared minus b squared.
So
it's not.
That's right. In region 2, you're right. In region 2, that's correct. In region 1, it's this plus. In region 2, it's a minus. Yeah.
Then my potential analogy is not because there would be an a squared plus b squared.
Yeah. So the analog of energy in region 2 is not a positive definite quantity.
But I was thinking just the probability current.
There is a flux conservation.
That has a minus sign.
There's a minus.
Because the probability current will have.
There is flux conservation in region 2, but yeah, there is a.
Wait, flux going in should be flux going out, right?
Yeah.
So suppose we have a solution which is flux going in only one place. That should be the sum of flux going out both places. Now, flux going out is not proportional to a squared in one place, mod a squared and b squared in the other place.
All I'm saying is that there is a there is a minus sign.
So flux is coming in, probability is coming in one of those out surfaces.
Yeah.
That's something strange.
It's to do with the fact that t is not a time coordinate in region 2. So the thing that's naturally conserved is not analogous to energy. It's more analogous to momentum.
No, but because it was analogous to momentum, I was using quantum mechanics. It's e by k, it's by minus okay, and then still you have mod a squared is minus. Yeah.
These are really creation and annihilation operators, right? So you should think of the operator multiplies e to the minus I omega as a destruction operator, and the other guy is a creation operator. So the relation really looks like b is equal to a plus b tilde a dagger. And therefore, the correct relation you need is that a square minus b square is 1. Precisely because r star is a time coordinate.
Yeah, there is a difference between 1 and 2.
That's something basic I was saying wrong.
Yeah. Okay. Good. All right. So since we've agreed to continue, maybe I should have a cup of tea.
Please.
Well, you work your visitors hard.
You want some biscuits?
No, I'll just drink the tea while I.
this thing.
Okay, right. All right, so we were going to solve the problem in region 1 now, aren't we? So, in region 1, so we need to define some more mode functions now in region 1. So in region 1, we're going to define R in plus and R out plus in exactly the same way as we did in 2. Okay, so we don't need to discuss them again. But we now also need to define some modes defined by their behavior near the cosmological horizon, which I'll call R in C and R out C.
Check with him if he doesn't want to. No, I mean, he might have some other conflict. He teaches actually.
Yeah.
Abhijit is teaching?
No, I'm wondering, I know he teaches in the morning now. No?
Oh,
And I'm not
maybe
sure.
we should then stop.
Then let's stop.
Okay.
He does have 11:30 teaching on some day, but I don't know what day that is. I don't remember.
Neither do I. But he does teach on Sundays. Yeah.
Math is today? Yeah, if he's not to teach,
Yeah.
otherwise I'll go.
It's better to stop.
I'm going to take my instructions from the director.
I have no say. That's not anything else. No, everyone else is the master of certain.
So what is the consensus?
You can give him a minute. One of the students has just gone to find out.
Ah, okay, okay.
Can you, if he's teaching, then I think we should.
Okay.
I'm sorry about.
Well, no, well, it's fine. I mean, I'm getting through more than I expected, actually.
This is great. I mean, it's really clear. Thank you.
Good.
It's very clear.
Good.
Actually, I'm also confused about this integer location of the poles.
Mhm.
I mean, like for quasi-normal spectrum, in BTC, of course, it's an integer space thing, but everything.
But these are not the quasi-normal modes. These are some unphysical things.
There's some
I-
not
okay.
It's like it's a class.
Yeah.
Okay. Well, you saw the schedule.
I mean, this is schedule. It's
Yeah.
on the schedule.
Yeah. No, I think he also did disappear very fast, so probably yeah.
Okay.
Sorry,
All right.
please,
Let's.
I'm
Yeah.
sorry,
Okay.
Sandeep.
Yeah.
No, 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 it's my fault. But I'll try to catch up on Friday.
Okay. Fine. Fine.
Great.
Very good.
Okay.
No, tomorrow is
11:30.
11:30 is 8066. And then day after tomorrow is today could have been no. I suppose the reason we didn't make it 11:30 today is because Abhijit has a class. That's probably the.
So one day today.
Yeah.
Okay. Good.
That's great. Well, very nice.
All
to
right.
have you here.
Oh, well, thank you, Sandy.
So you,
Okay. Oh.